we've already met a whole bunch of functions that cannot be integrated. Things like e to the x squared or cos x over x, they don't have an elementary function integral. And yet we may still be interested in finding the area enclosed by those curves. More generally, in a lot of real-life situations, we're dealing with either functions that we don't know how they're created. We've got a graph of some data and we're trying to fit functions to it. Maybe they don't work so well. Or perhaps we have functions that are so complicated that they will be very difficult, if not impossible, to integrate directly. However, if we don't care about the general integral result, if we only care about a specific definite integration between two limits, then we can find a pretty decent approximation for the area enclosed. In this case, for instance, we've got the speed of a car as it goes around a track. You can see that around 6 seconds, the driver starts braking heavily in order to go around a tight corner, presumably, and then accelerates up again between about 10 and 20 something seconds until he gets to the next corner. Now, there's no obvious function that we can use to map this. You might start messing around with trig functions and other periodic functions combined with other things to try to make a fitting for this, but generally speaking, that would be a whole lot of work, and you'd need to make a whole new version for every single different bit. There's no reason to believe that the speed the driver has chosen to go at should fit very nicely any particular mathematical function. It's not as if it's being driven by a physical law like the motion of a planet. So we're kind of stuck. There's no obvious function we can use, and yet we'd still like to answer questions like this one. How far does the car travel during the first 15 seconds? Well, this is a velocity time graph, so that question is essentially the same as asking for the area under the curve between 0 and 15. What I'd like you to do is pause the video and give yourself 2 minutes. So don't go beyond the 2-minute limit. See how accurate an estimate you can come up with for this graph for the area between 0 and 15. When you've done that, ask yourself this question. If I'd given you more than 2 minutes and requested a more accurate result, could you have done it? What sort of improvements would you have made to your method that might give you a greater level of precision? Where does your approximation method overestimate or underestimate, and how could you mitigate for that? In general, it's important to remember that numerical approximations don't even attempt to give us the correct answer, but that's rarely what we actually need. It's not necessary to know exactly how far this racing car traveled, but we need to know roughly how far. And depending on how precise we need to be, we can improve the precision of our estimate arbitrarily. We can make it as precise as it needs to be. You need to know how far you travel to the nearest meter, we can do that. If you want to know how far you travel to the nearest centimeter, well, we could do that. It'll take a bit more work, but there's nothing stopping us from zooming in on this graph and taking each piece bit by bit, taking sufficiently many steps to give us a sufficiently good answer. It doesn't need to be perfect, it just needs to be good enough for the application that we have for it. With pretty much any process, any calculation, any project that you're doing, you will come across this phenomenon. Good, fast, cheap. Pick any two. Especially if you're looking at a computing project, you will see this come into play quite a lot. You can have a bit of software that is good and you can make it quickly, but it will be expensive to do so. Or you can make your program good and you can make it cheap, but it will take a long time if you want to do that. Or you can have it fast and you can have it cheap, but if you do that, then chances are the quality is going to be impacted. So there's always a trade-off between these things. You cannot maximize all of them at once. And with numerical integration, we also have a trade-off. We're looking at the precision of our answer as opposed to the amount of legwork that it takes to get there. And from a human perspective, we're talking about how many calculations you need to do or how much time it takes you. But also from a computing perspective, where most numerical integration will take place, it's a question of how much computing power you want to put in order to get back an answer as accurate as you need it to be. So if you don't need 15 decimal places of accuracy, it may well be that you can save yourself quite a lot of computing time, which is essentially saving you money. Let's start with the most basic approximation, a straight line. There are all sorts of advantages to using a straight line. We can do even better if we decide to use a series of straight lines. One of the big disadvantages of assuming a curve is a straight line is that most curves are wildly different to straight lines. For short periods of time, they might be closely modeled by a straight line, but if you want to get any kind of sense of the long-term behavior of a function, unless that function is pretty much a straight line, you're going to need something a bit more sophisticated. But we get most of the advantages of straight line modeling through a series of straight lines. We can build the model quickly because all we need is the endpoints for each line, and we can calculate using the model quickly as well. We can integrate, we can consider the area underneath a straight line without even needing to use the techniques of integration. We can look at each piece as a straightforward looking polygon. In fact, each one is just going to be a trapezium. So here's the coordinates of these points. I'm looking at that section of the graph from 0 to 15 seconds, and I've just picked a couple of suitable looking points. I've not tried to break the interval into equal spaces for this, although in general that's the kind of thing that Trapezium Rule does. What we're going to do is try to sort of build it up for ourselves. So I've chosen suitable-ish looking places. We've said this first section from about 0 to 6 seconds looks like it's pretty much going to be a straight line, or a straight line model will work quite well, and we do a similar thing for the next 3 seconds, and then for the final 6 seconds that's its own straight line again. Have a go using the information that I've provided for you, those 4 coordinates, and see if you can find an approximation for the area. You might want to compare it to the approximation you found earlier and see if you prefer this one or yours. Pause if you want to have a go at that, and then come back and I'll show you the results that I've got. So we have our approximate value going to be taking advantage of the fact that each of these straight line segments corresponds to a trapezium, and we can calculate the area of a trapezium either directly using the average width times height formula, half a plus b times h, or you can break it into a rectangle with a right angle triangle on the top. I get an approximation of 823.5 meters using these 4 points. And you might be interested to know that the true answer, which essentially is still using numerical integration, because this is not a function that you can construct mathematically, as far as I'm aware. I drew it literally by tracing my finger over the screen on GeoGebra, so it is a freehand diagram, and yet GeoGebra can still integrate it, and the way it does it is pretty much this technique. It breaks it into lots of thin pieces, more than 3 thin pieces, and it gives a pretty accurate answer for the area underneath the curve. It's almost certainly going to be accurate to within about a meter or so. In this case, our 823.5 was still only 3% away from the true value. So if you want a ballpark figure, you can take even just a small number of points, model the curve as a series of straight lines between those points, and you'll get a remarkably decent approximation for the true area. The next thing we need to do is set up some notation. We want to find a way of describing the various pieces that we're going to be talking about so that we no longer need to think about the process of finding the area for a whole bunch of different shapes. Behind the scenes, it's going to be trapezium area formulas that are used to build this up. But we want to make this into a general formula that will do the whole thing for us. And it might be a big, messy looking formula, but it should be something that takes the grunt work out of the process for us to some extent. We're looking to find an approximation for any integral we want to do. Anything where we can't necessarily integrate the function, or perhaps we don't want to because it'll be too time consuming. We have a function which I've called y, which is a function of x, integrated with respect to x between the limits of a and b. The best way to make sense of this is through a diagram. So take your time to look carefully at this diagram and make sense of the different pieces. We have, first of all, the thing that might look surprising, h, height. Well, if you think about the trapezia that we're looking at, each one of them looks like it's a different way round to the more standard traditional way of drawing a trapezium. we would usually have the two parallel sides horizontal, whereas here they're vertical. That means that the thing we normally call the height of a trapezium, which we still want to call height here so that we don't get too confused, that thing is now tilted on its side and is the horizontal distance between the two parallel sides rather than being the vertical distance between the two parallel sides. Now, the next thing to notice is the x-ordinates. That's like half of a coordinate. The coordinates are the x and y ordinates of a particular point. So these values are just the x values that correspond to coordinates on the curve. That means that x naught in this diagram is just 1. Not 1, 2.7, but just 1. And then x1 will be 2, and so on. You might notice the numbering. This will remind you of how it works in programming if you've done anything with code. x0, x1, x2, x3, and x4 correspond to the 5 ordinates, but starting from 0. So indexing at 0, so your very first term is the 0th term, can lead to a bit of confusion. We have 4 strips. You can see the 4 different trapezia, and yet there are 5 ordinates. You can even see their values 1, 2, 3, 4, and 5, but you can also number them as x0, x1, x2, x3, and x4. So your 5th ordinate will have a value of, in this case, 5, but it will have a name of x4. In that way, we find that the final version, the final ordinate, xn, represents n strips. We've got x4, and there are 4 strips. The y ordinates are the corresponding values that give us the height of each of the parallel lines. So the first trapezium has parallel lines of height y0 and y1, and the next one y1 and y2. You can think of them as the y coordinates of the points on the curve that we're connecting up with straight lines, or you can think of them more usefully as the distance vertically upwards from x0 to the curve, from x1 to the curve, and so on. A couple of things to notice. If we want to integrate between a and b, then x0 and xn are a and b. Those are the end points. So if you've got n strips, like we've got 4 strips, then x0 will be your lower limit for the integral, and x4 would be your upper limit for the integral. And the other thing to spot here is that as soon as you know what the 2 limits are for the integral, and you've chosen how many strips you want to use, you can immediately calculate h. It's fairly obvious in this particular case. If we want to integrate between 1 and 5, then the size of the interval is 4. 5 minus 1. That's the length of the gap from the beginning to the end. If we divide that by the number of strips, in this case we've chosen 4 strips, we get a height of 1. If we chose 8 strips, we get a height of a half. So we get thinner trapezia, checking in with the function more often, giving us a more granular, detailed viewpoint on the integral, and therefore a more accurate answer. We wouldn't get the large discrepancy you can see creeping in halfway through the first strip. We've got the line undercutting the function quite a bit, and halfway through the last strip, you've got the line overshooting the function quite a bit. Those discrepancies, the overestimates and the underestimates, will be minimized if you use a larger number of trapezia. And that's what happens when you increase the size of n. You will decrease the size of h, and you'll have more trapezia, but they'll be thinner. This quite daunting looking table is just a summary of all of those things. So y and a and b correspond to the original integral that you're dealing with. Then n is the number of strips that you choose to split the region into. In an exam, this will be given to you. They'll tell you to use 4 strips or 8 strips. And often, for Edexcel, they also provide you with a table to make it easier to structure your answer, to put your x ordinates and your y ordinates in together. H is the height of each strip, but we're looking at it sideways, so that's the horizontal distance between any x ordinate and the next one. And then we've talked about the x ordinates and the y ordinates themselves. So let's bring this together now. Use this picture and this notation to build for ourselves a formula. We're going to start by constructing a formula specifically for 4 strips, but you'll see quite quickly as we build it up how this could very easily be generalized to any number of strips you like. So we'll start with this key idea. The trapezium area will be the average width multiplied by the height. Now in this case, when we talk about width and height, we're thinking of a trapezium that's turned the other way to these ones. So the average width would be the average of the length of the two parallel sides, and then the height will be the perpendicular height vertically between the two parallel sides. So see if you can interpret that within the context of this notation. Work out the area of each of the four trapezia. When you've done that, you can continue watching the video and we'll see if we've got the same results. The other thing to notice is that we have n strips, and if we've got n strips in general, then we can calculate h, b minus a over n. Let's look at the first trapezium. The average width of the trapezium is going to be y0 plus y1 over 2. So the average of y0 and y1. And then we multiply by h, which is the height of the trapezium, and that gives us the area. We do the same thing for the second trapezium, but with y1 and y2, and you can start to see not only why it's repetitive, but also why it will combine relatively nicely into a general formula. Every single one of those terms has a couple of things in common. All of them have got this dividing by 2, because we were averaging the lengths of the two parallel sides, and all of them have a multiply by h because we were multiplying by the height of each trapezium. So if we were going to add those together, we could pull out as a common factor both h and a half. And here we are. There's another thing you might notice. We've got a single y0, but we've got two lots of y1, two lots of y2, two lots of y3, and then just one of y4. If you're wondering where all of those extra ones come from in the middle, well, if you look closely, you'll see them appear in more than one trapezium calculation. y1, for instance, is the length of the rightmost parallel side in the first trapezium, but it's also the length of the leftmost parallel side in the second trapezium. So because it contributes to two of these, it ends up appearing twice in the formula. And the same thing will be true for y2. It appears in the second and third trapezium, and y3. So we have repetition for all of the inner y ordinates. The only ones that only appear once are the end ones. So y0 appears once, and y4 appears once. Everything else appears twice. You'll have two copies of y2 because it appears in those two, and two copies of y3 because it appears in those two. And this is the trapezium rule. Well, this one is the trapezium rule for 4 strips. You can see how it would extend quite nicely to n strips. We're always going to have this repetition of the inner y ordinates. So we just need one copy of the very first y ordinate, y0, one copy of the very last y ordinate, yn. In this case we have y4, but in general yn. And then two copies of everything else. All the other y ordinates get put together, and you have two of those, and at the end you multiply the whole thing by h over 2, multiplying by h because every single area formula has an h in it as a factor, and multiplying by a half for the same reason. In general, it's worth noticing this trapezium rule overestimates the integral wherever the curve is convex and underestimates when it's concave. We'll come back to this idea a little bit later as well. We'll look into it in more detail in the bonus section at the end of the video, but for now it's worth looking carefully at the picture we've got and noticing the convex sections of the graph. For instance, between 1 and 3, between x0 and x2, you can see the curve is convex, the gradient, between x0 and x2 the curve is concave, so the gradient is decreasing, and we can see that trapezium rule gives an area which is clearly too low. There's a gap. The trapezium gives a smaller area than the actual area under the curve. And then when we get to the next half of this curve, between x2 and x4, the curve is now convex, the gradient is increasing, and therefore trapezium rule is overestimating. It's worth having a think and drawing some pictures for yourself. This will always be the case. Anytime the trapezium that you're drawing is drawn over a bit of the graph where the gradient is increasing, the straight line model will overshoot the curve. And wherever the gradient is decreasing, the straight line will undercut the curve. Worth noticing that the formula for the trapezium rule is provided in the formula book. It's right at the bottom of the integration section because it is a method for finding integrals essentially. It's an approximation. You'll notice there's no integration required within any of this. That's the whole point. Even for a function that you cannot integrate, we can still find an approximation for its value by applying this rule. All we need to be able to do is calculate the value of the function at any particular point, not the value of the integral. That's what the whole rule is designed to show you. Let's try an example now. And I've deliberately chosen for this one an impossible integral. Cos x over x is something which you cannot find an elementary function to describe. And we're going to see if we can estimate the value of it using trapezium rule with just 4 strips. It won't be the most accurate estimation in the world because we're only breaking it into 4 trapezia, but it'll show us the general principle. What we do at the beginning, we start by finding the formula. So you can look it up in the formula book. It's usually a good idea to write it down, but if you write it down, I'd recommend you write it down specific to your particular situation. In other words, if you've got 4 strips, then when you write this formula, you would replace the n with a 4 wherever it appears. We can also write down a few quick things at the very beginning. We can say that a is 1 because that's the lower limit, b is 3 because that's the upper limit, n is 4 because that was provided for us in the question, and finally h equals 0.5. Now there's a bit in the formula book that says h equals b minus a over n, but in general that's something that we should recognize and understand anyway. We're trying to split an interval which goes from 1 to 3. In other words, it has a length of 2, and we're sharing it between 4 strips. So 2 divided by 4, that gives a height of 0.5. There's another way you'll be able to verify the height. As we start calculating the x ordinates, then the height value is what we add every time to get from one to the next. We start with x0, which is of course the same as a. So whatever that value is, that's the same. And then we add h, and that gives us x1. These, we don't even need to look at the function at this point. If we're doing any integral between 1 and 3 with 4 strips, we'll always have the same x ordinates. 1, 1.5, 2, 2.5, 3. And if you get to the end, if you get to 3, and you've got the right number of ordinates, then you've obviously been using the correct value for h. The whole point of h is that it breaks the interval down into the appropriate steps. And it's a good idea to write these carefully and have space next to them because we're going to be calculating the y ordinates based off of these x ordinates. We do that one at a time. y0 will be cos of x0 over x0. So we're applying the formula directly from within the integral. That's the original function that we were trying to find an estimate for the integral of, cos x over x. We put 1 into that and we'll get some value, some awkward decimal, like as not. If you get something relatively nice, like pi by 3 or ln2, then feel free to write it in that exact form at this point. All that matters is the most precise values possible go into the formula when we get round to it. You'll notice I've not truncated this or rounded it. I've written the first few decimal places of it, and then I've put a ... afterwards. That indicates that although I'm writing down something which is similar to the number, I am thinking of and trying to represent the exact value, which is not something I can write down, but maybe it's something you can store in your calculator for later. We'll talk about that in a moment. We can do the same with y1, cos of 1.5 over 1.5, y2, y3, and y4. And once we've found all of those values, we've got everything we need to go into the formula. Notice that these 3 bits here correspond to these middle pieces inside our original formula. Those are the inner y ordinates. So instead of being the very first or the very last, they're the ones that get shared by 2 different trapezia. And then these endpoints here correspond to the endpoints here. So we'll take 1 copy of the purple ones, and we'll have 2 copies of the green ones, put them all together, multiply by h over 2, and we're done. So it looks messy. There's quite a lot of numbers having to be written in there, but as long as we're using the most exact values we can here, we're not just writing in 0.540 and minus 0.329. We're using the most precise values we can from our calculator. then what we should find is that the final result we end up with, when we put it all together, is negative 0.188 to 3 significant figures. You'll notice at this point, I round, and not before. The rounding only happens at the very end. So you might even want to write down a more precise answer. It won't necessarily be more accurate though. It'll be more precise, it'll have a greater number of decimal places, but it won't necessarily be any more accurate because remember, this whole thing is an approximation. At this point, you might find it helpful to grab your calculator and find the integral button. There is a button which does exactly this process, numerical integration. The difference is it doesn't let you specify how many strips you're going to use because it assumes you want the most accurate value you possibly can. So it will use however many strips it needs in order to give you an answer which is accurate to the number of decimal places that it can display. So the class whiz cannot tell you what cos x over x integrates to exactly because it cannot be done. But it can give you an answer numerically to whatever level of precision you really need. Your calculator to the level of precision that can be displayed on the screen, but something like Wolfram Alpha to as many decimal places as you might request. Presumably there's a limit, a few hundred decimal places or something, but it'll be accurate enough for whatever practical purpose you need, even if it's not an exact value. You'll notice we've got about a 10% error margin here. So from approximately 0.19, which is what we got, to about 0.22, it's not far off. It's not bad. Remember, we only used 4 strips. And if you want to see what it looks like, this is the GeoGebra version of this curve. It's quite a curvy thing, and it's reasonably well modeled by straight lines here, but you can see where the 10% error comes in. There is an overestimate for the first strip, and there are some underestimates for the later strips. So, although it looks pretty good, and it's pretty reasonable, it's not going to be perfect. You can also see that this gives us a negative. And although we didn't consider weird things like that second strip, that doesn't even look like a trapezium. It looks like 2 triangles, one above the axis and one below the axis. And yet somehow our formula works just fine even for those. It will work fine for negatives. If you think about the third strip between 2 and 2.5, that gave us a negative value for the beginning and for the end. So y2 and y3 were both negative. But if we combine those and still use the standard trapezium formula, all it does is give us a negative value for the area, which is actually fine because that's exactly what integration is supposed to do, to treat area below the axis as negative. Not only that, but if one of your parallel sides is positive, like y1, that's this little one here, and the other one is negative, like y2, well, the trapezium formula is not phased by that either. It can still get the average width, and it can still multiply by the height, and it will still give you the area, and it will perfectly correspond to the area you would get if you were integrating that straight line. In other words, it'll treat the bit above the axis as positive, it'll treat the bit below the axis as negative, and put them together. So it just works. It does what it should do without us worrying about the detail. Here are the steps you should generally follow. They might be worth writing down. The first thing you do is you jot down the values of n, a, b, and h. H you calculate from a, b, and n, but it should be relatively intuitive, and there's also a formula for that right next to Trapezium Rule in the formula book. Step 2, you write down your x ordinates. You make sure they're nice and clearly listed. If you've not got a table provided for you, you'll probably have to write these for yourself. Step 3, you calculate the y ordinates. These are using the function within the integral and the x ordinate that corresponds. So y2 will be using the value of x2 and so on. Next, you substitute your numbers into the formula. You want to use, as far as possible, exact values. And then finally, you check your answer. This is kind of optional step, but it can be really useful, especially if you want to check that you've done it right. Lots of mistakes can creep into this, especially if your structure isn't particularly good. But if you check your answer with the class whiz, you can verify that the number is what it should be. And the last thing I want to say is actually related to the class whiz. What I often do is store these values as I go along. You've got quite a few different spots on the calculator to store values. Try the STO button. If you press STO and then any of the buttons that have got a capital letter over them like A, B or C, then you should be able to store the value that's currently shown on your calculator display into those places. If you use Shift and STO, then you can recall those values. There's a few other ways to do it as well. That would have the advantage of giving you a slightly simpler thing to write down at the end. You can then take advantage of the algebra you've introduced. So we want the ends, A and E, plus two lots of the middles, B, C, and D, and then we just want a half over 2 multiplied by that. That is perfectly acceptable. As long as you've got the number written down in some form, in some approximate form previously, then you can, by all means, state that you've saved them in the calculator and then use those saved versions. The next example we want to look at, I quite like this one. So weird sort of graph. You might want to try to visualize what it would look like for yourself. But it's also something that is not particularly easy to integrate directly. There's a standard function for this, but it's not one we've come across yet. It's something you'll investigate a bit more when you get to further maths. But we're going to try to find an estimate for the value using 4 strips and then using 8 strips. We're only going from 0 to 1, so if we have 4 strips, hopefully you can already see that's going to give us a height of 1/4. Then if we decide to use 8 strips, that'll give us a height of an eighth, 0.125. So let's start with this, A and B, 0 and 1. If n is 4, then h is 1/4. We're just splitting the interval of 1 between 4 strips. We write down our x ordinates. We should have everything from 0 up to 1 going up in jumps of 1/4. And remember, because we have 4 strips, there will be 5 x ordinates, numbered from 0 to 4. With each of those, there is a corresponding y ordinate, and we're just substituting in the value that we have for the x ordinate. So 4 over 1 plus 0 squared, 4 over 1 plus 1/4 squared, and so on. It's not necessary particularly to write down this intermediate step. You don't have to write y0 equals 4 over 1 plus 0 squared if you want to just write 4. But it can be helpful if you've got a bit of extra structure to help you spot if there's a mistake somewhere. You'll notice for these, I'm not saving these values in my calculator. I'm writing them in exact form because each of these has a nice exact form. 3.2 and 2.56 are exactly the correct values. And for 64 over 17, because the calculator allows me to get a precise value as a fraction, I'm going to leave it as a fraction. And that means I'm not losing anything in terms of precision when I take these numbers. Then we put them into the formula. We've got the two ends, 4 and 2, they appear here. And then we've got the middle bits. All of these pieces go in there. We have 2 lots of that. We multiply by the height over 2, and we get 3.131. I'd encourage you at this point to pause and see if you can calculate a few extra values. You can use these ones plus a few in between to find an approximation with 8 strips. When you've done that, unpause and you can compare your answers to mine. Here's what I got for 8 strips, and as a bonus I've given you the 16 strips version as well. If you use the table mode in your calculator, that's menu option 9, you can type in the function you want to apply along with information about the range of values you want to put in. So it'll give you a starting value, an ending value, and the increment. You'd use 0 and 1 and 0.25 or 0.125. And then the calculator will give you all the values in a table. You can then scroll through them one by one and perhaps save them. Depending on how many you've got, it might be quicker doing it like that. It might be a bit more tedious. But when you've got your values somewhere, you can add them together. You can combine them with the formula and get your result. We got 3.139 and 3.141 for 16 strips. And if you've done a test with the class whiz using the integral of something button, the numerical integration function, then ClassWiz doesn't just give you 3.14 something, it gives you the number pi. Now the calculator doesn't know whether something is exactly pi or not. It can't, because pi is a number which cannot be represented in a finite number of bits inside a calculator's memory. But what it does is compares the values it gets to the value it has stored for pi. And if they match to the level of precision the calculator has, then it's going to assume the answer is exactly pi. maybe it's not quite right. But in this case, maybe it is. Maybe there is a reason that the integral of 4 over 1 plus x squared between 0 and 1 is exactly pi. It's also worth noticing that we get a 0.3% error even for just 4 strips. This particular function is represented pretty darn well even by 4 strips. There is a slight underestimate that you can see at the top, and there's going to be a slight overestimate for a couple of the other strips later down. But overall, it seems to sort of cancel out quite nicely. And this curve doesn't do anything crazy. Most of that interval, it's a relatively constant gradient, which means there's not a huge amount of variation, and you're not going to get a massive amount of over or underestimates. That's why we get such a high level of accuracy for our estimate. If you're curious about the pi, I'm not going to go through it here, but if you try differentiating arctan x, that might give you a bit of a clue. You'll start to see how that function is connected to this integral. The derivative of arctan x is not something you need to worry about particularly. It's part of the section that was left in the differentiation chapter by mistake in the early textbook editions. It's something I've got a bonus video on if you want to look it up, but if not, don't panic. You don't need to remember what the derivative of arctan is. What you do need to be able to do is the exercises from 11L. So try the questions in that exercise. You'll notice that a lot of them provide you with a table so that you don't necessarily need to list all the x ordinates and y ordinates and double check everything for yourself. There'll be a bit of structure in there provided for you. It's worth being aware of. That's not necessarily the same with other exam boards, but certainly for Edexcel in general, if they give you an exam question on this, they're not trying to trip you up with the notation. They're not trying to confuse you. So if they say we're going to use Trapezium Rule with 4 strips, they may even include in brackets 5 ordinates so that you know there's going to be 5 values of x that you calculate and 5 corresponding values of y that you calculate. But to make your life a bit easier, they often provide you with a table, and they might even fill in some of the values for you, some of the x values, maybe even some of the y values, just so that you're being tested on the process and the understanding of it, but not so much on the nuts and bolts of what goes on within constructing the formula. All the routine stuff they're trying to take off your plate a little bit. So that's quite nice. What they will do is give you additional marks for some slightly more conceptual questions. They'll be asking you about how the approximation works, when it may not work so well, and what kinds of results you might expect to get. They'll say things like, state whether your estimate is an overestimate or an underestimate, and explain why. And that will involve a diagram, thinking about whether the curve is convex or concave. The best way to explain it is by drawing a little piece of the curve and justifying it directly from a nice clear diagram. Show why a straight line approximation for a bit of the curve is going to overshoot or undercut the curve. Welcome to the bonus section. We're going to look at a few more interesting functions that we can investigate using Trapezium Rule, and we're also going to get a little bit of an insight into a few additional methods for numerical integration. The alternative rules that we're going to look at are not necessary for the course, they're not on your specification, but they give you an interesting insight into the alternatives that are used to calculate more efficiently, perhaps, the area under a curve. We're going to start by looking at the normal distribution. It's a classic example of an integral that cannot be calculated. We cannot integrate e to the minus half x squared. And yet, it's also really useful to do precisely that. The whole purpose of the normal distribution curve is finding the area underneath it. If you find the area under the curve between 1 and 2, it should give you the probability of a continuous random variable taking a value between 1 and 2. Now, this particular curve I've shown on the screen isn't the normal distribution curve. It isn't any normal distribution curves, because any normal distribution curve, including the standard normal distribution and any other version with different means, different standard deviations, in other words, translated horizontally or stretched or squashed horizontally, none of those are this curve. The reason I know that for sure is that the area under this curve looks like it's quite a bit bigger than 1. You can pause and convince yourself of that by looking at the values and doing a rough estimation. But that means that whatever the area is under this curve, we're going to need to shrink the curve down so that the area becomes exactly 1. We need the total probability, the total area from minus infinity to plus infinity to be equal to 1. To get that, we need to know the area under this curve. And to do that, we can use Trapezium Rule. Now, we're going to start slow. We're going to begin with 0 to 3 instead of 0 to infinity. And we're going to use just 3 strips. So it'll make life nice and simple. We'll go 0 to 1, 1 to 2, 2 to 3. If you want to follow along, you can pause at this point and calculate the estimate for that integral. Or if you just want to watch and see what I get, then that'll be almost as good. The first value, e to the 0, and the last value, e to the minus 9 over 2, they're the endpoints. And then the middle terms in here, e to the minus a half and e to the minus 2, those get dealt with twice because they occur in both the trapezium on the left and the trapezium on the right of that y-ordinate. Now we get a value of 1.247, which fits with my idea of the entire curve having an area quite a bit bigger than 1. Looks like even just the right-hand side has an area bigger than 1. Now, if we look at the diagram for this, hopefully we'll notice a couple of interesting things. One of the things that you might notice is that the curve shrinks down towards an asymptote so quickly that beyond 3, it's almost indistinguishable from the x-axis. That means that the area we're approximating from 0 to 3 is pretty much the entire area from 0 to infinity. There'll be a few bits that we're not quite seeing. Obviously it goes a long, long way beyond 3, but because it's an exponential decay, and it's a very fast exponential decay because of the x squared, we're going to find that the curve shrinks very quickly, and just getting a relatively short interval for a finite area will give a pretty good approximation for a much larger area or a much larger interval. The other thing to notice here is that some of the trapezium strips underestimate the area and some of them overestimate. You might remember that there is a point of inflection at x equals 1 on both the standard normal distribution curve and this one. The standard one, remember, is just a scaled down version of this, a y stretch, which means it doesn't affect the x coordinate of any stationary points or any points of inflection. If you differentiate twice, you can identify the moment when the concavity changes. The curve is concave from 0 to 1, but it becomes convex at the point when x equals 1, and from then onwards, for the next 2 trapezia, we're getting an overestimate instead of an underestimate from Trapezium Rule. Well, the nice thing about this is Trapezium Rule gives an underestimate followed by a couple of small overestimates, and overall those are going to cancel out quite nicely. They compensate for each other, and that means that we're getting a pretty decent overall approximation for the true area under the curve. Whatever that might be, 1.247 is not far off. The next thing to notice is that because e to the minus 9 over 2 is so small, even within the Trapezium Rule, if we start throwing a few extra terms in there that are even smaller, they're not going to have much effect. So what if, for instance, we decided to investigate a wider interval? If we look from 0 to 6. To keep things simple, I'm not going to change the width of each strip. So if I went from 0 to 3 with a height of 1, I'm now going to go from 0 to 6 with a height of 1, which means I'll have 6 strips. That also means I can reuse many of my values. So for instance, e to the 0 is still there, e to the minus 9 over 2 is still there, but you'll notice now it's one of the middle terms instead of one of the end terms. We've still got e to the minus a half and e to the minus 2, but in addition to that, we've got a few extra ones. We've got e to the minus 8, e to the minus 25 over 2, and e to the minus 18 tacked on the end as well. All of those are very, very small numbers. And if we decided to go even further, 0 to 8 with 8 strips, or 0 to 20 with 20 strips, all we'd be doing is adding smaller and smaller values. Since they don't make much difference, the overall answer is very similar. 1.253 as opposed to 1.247. Not very much difference in there. That gives us the additional confidence that integrating over a relatively short interval gives us a very good approximation for the total area under this curve. Now, it's by no means obvious that the integral from 0 to infinity will be a finite value, but it certainly looks that way from what we've got here. The proof of that is something you'll get onto if you do further maths, but it's, in a way, it's reminiscent of geometric series, where you can find the sum of the first 10 terms or the first 20 terms, but if you notice that there's not much difference, then it's an indication that it might be possible to find the sum of all the terms, s infinity, and still get a sensible finite value. Here's what the graph looks like if we integrate from 0 to 6. And you can't see any difference between this one and the one above, because the area between 3 and 4, and between 4 and 5, and between 5 and 6 is so small, it's off the chart. We can't even detect the difference between the curve and the x-axis here. With that 1.253, which we're now reasonably confident is pretty much the area of the entire right-hand half of the curve, I'd like you to try something for me. I want you to square it on your calculator and then double your answer. See what you notice. Now, your calculator probably gives you this answer, pi. Now, if you've learned to be suspicious of calculators and computers, then you might be wondering if this is a real pi or if it's just that the value that the calculator has managed to construct is so close to pi that it can't really tell the difference. This is by no means a proof that the area is related to pi, but it's certainly an indication that there might be something in it. And I'm not going to attempt to demonstrate why this is exactly true, but it turns out it is true. Turns out, if you integrate between 0 and infinity, you get the square root of pi over 2, 1.253-ish. We can write this a little more nicely by rationalizing the denominator. We get root 2 pi over 2. The entire thing is square rooted. The square root of 2 pi over 2. And that means we can integrate the entire thing now. We've got the symmetry because it's an even function. The only powers of x that appear are x squared, so it'll give the same for negative values of x as it does for positive values of x. You'll remember that's a key feature of the normal distribution anyway, the fact that it's symmetrical. And that means the total integral, the overall area from minus infinity to plus infinity, will be just 2 times this. It'll be root 2 pi. And therefore, we can squash it down, as is shown up here in blue. The normal distribution has a total area of 1, and we can make that happen by dividing our function by root 2 pi. The next thing I'd like to do is investigate some alternatives to Trapezium Rule. We picked out Trapezium Rule from looking at what happens when you model a curve as a series of straight lines, and it works pretty well. To be honest, in most situations, it will give you a perfectly sensible result. And if you want something more accurate, you simply increase the number of strips. But it does have a few drawbacks. Let's look at what's wrong with it and see if we can find some method that doesn't necessarily have the same drawbacks. For a start, it gives us a value which is too high whenever the curve is convex. It's going to overshoot the curve and therefore give us a value which is bigger than the true area under the curve. And vice versa. If the curve is concave, then over that interval, Trapezium Rule is going to underestimate. Whenever the curve has a decreasing gradient, a straight line model will undercut the curve and the area of the trapezium will be too small. The other thing is that it doesn't fit extremely curvy functions particularly well. I'm aware this is not really a technical term, but think about a function like cos of e to the x. And if you can't think of it very easily, try drawing it on GeoGebra. It basically wobbles up and down faster and faster as x increases. And there's a lot of change in gradient. If the gradient changes rapidly over a short period of time, then that means a straight line is not going to be a very good fit, because the whole idea behind a straight line is that the gradient is constant. And even if you've got lots of small intervals, if there is a large change in gradient over a short space of time, then a straight line model may not be the best way to deal with that. You can see these drawbacks directly from this graph. I think this is the graph of x plus 2 sine x. For the concave intervals, say between 1 and 2 and between 2 and 3, you can see that the curve is underestimating. And for the convex intervals between 3 and 4 and 4 and 5, the curve is overestimated by Trapezium Rule. If you're lucky enough to have an interval that covers a similar quantity of convex and concave intervals, then these will mostly cancel out and you'll still get a reasonably good approximation. But it's unlikely that this will always be the case, and it's certainly not something you can assume. So let's see what happens with an alternative approach. The mid-ordinate rule is not actually more complicated. In some ways, it's a simpler idea. It's based on rectangles rather than trapezia. So instead of trying to work out the area of a trapezium between 2 points, it's looking at the area of a rectangle whose height corresponds to the height of the function somewhere in the middle. It's about twice as good as Trapezium Rule because it does a better job of taking into account where the function goes in between two x ordinates instead of just looking at where it is at each end. However, it still has its own drawbacks. It underestimates for convex intervals and overestimates for concave intervals. You'll notice that's the other way round to Trapezium Rule. So mid-ordinate rule will give us a value that's too low whenever Trapezium Rule gives us a value that's too high. Well, that's quite interesting. The other thing about this, because it doesn't do anything to deal effectively with changes in gradient, it also doesn't fit the particularly curvy functions especially well. This diagram will help you to see more clearly how mid-ordinate rule works. The idea is you calculate the height of the function between the two x ordinates. That's why our y ordinates are written as y 0.5 and y 1.5 and so on. Y 0.5 is effectively halfway between x0 and x1 evaluated with the function. And if you look closely, you might be able to see, for instance, the strip from 4 to 5 gives an underestimate, and that is a section of the function which is convex. That means that the final half of the 4 to 5 interval has a curve which is quite a bit higher than the first half is lower. One half of the mid-ordinate rectangle will almost always be above the curve and the other half will be below the curve. And so effectively every single rectangle is compensating for its own over and underestimate. The question is, when is the overestimate of a particular rectangle bigger than its underestimate, and vice versa? And you can see from the diagram that we get an exaggerated version with mid-ordinate rule whenever the curve is concave, and an underplayed version whenever the curve is convex. And that is exactly the opposite way around to what Trapezium Rule does. So perhaps you're wondering at this point, is there a nice way to combine the two? I like to think of this as, imagine you've got two friends who are both pretty rubbish at guessing the price of things. So you say to one of them, how much do you think I spent on this watch? And one of them will underestimate some of the time and overestimate some of the time. The other one also underestimates some of the time and overestimates some of the time. But perhaps for certain products, your first friend always gives an answer that's too low and your second friend always gives an answer that's too high. And for other products, it's the other way around. It doesn't even matter if you don't know which products are which. You don't need to know which brands your first friend has a low opinion of and which brands your first friend has a high opinion of. All you need to know is that one of your friends gives an answer that's too low and one answer that's too high. What would you do in that case? Well, you might take the average of the two. If you take an estimate of £20 and an estimate of £30, you know that one of them is too high and one of them is too low. Well, chances are the product's going to be about £25 in value. The other nice thing about this is that it can also take into account how good the estimates are. Maybe one of your friends is underestimating by a lot and the other one is overestimating by a small amount. So you're going to want to guess a value that's lower than the overestimate, but not much lower. So somewhere between the two, but closer to the more accurate friend. That's what we would like to do with these. Somehow we want to take a bit of trapezium rule and a bit of mid-ordinate rule, but perhaps more mid-ordinate than trapezium because that's generally better. And yet we need some of trapezium rule because that will help us to compensate, to mitigate for the underestimates of mid-ordinate rule when mid-ordinate rule underestimates, and to compensate for the overestimates when mid-ordinate rule overestimates. Let's look at a third rule now. Simpson's rule. Simpson's rule is derived by modeling the curve at a series of parabolas. In other words, we build a quadratic graph that goes through points on the curve. This is a big advantage over straight lines because it provides a much better fit for the very curvy graphs. A quadratic, if it's a steep enough quadratic, can have a rapid changing gradient. And depending on which bit of the quadratic you end up fitting to the curve, you can have maximums, minimums taken into account. They don't have to mess up the trapezium or the rectangle that you've chosen to use because you're not using one. You're using a curvy shape to match a curvy shape. So it seems like it should work well. Now, the trade-off is that quadratics are less simple than straight lines, so they'll be harder to calculate with. But actually, we can integrate any quadratic really easily. So you could even start with ax squared plus bx plus c, and you can see that the integral of that is just going to be some function involving a, b, and c with x. It's not going to be complicated, it's just going to be a cubic. You'll have ax cubed over 3 plus bx squared over 2 plus cx. So pretty straightforward. And then once you've got those, if you substitute limits in, you can generate a suitable formula. It's a bit of a beast to produce, so I'm not going to go through the derivation here. You need to find a way first of constructing a quadratic that passes through 3 given points. And once you've got that, you need to find a way to integrate your given quadratic and combine them all. And you end up with something a bit interesting here. We have the endpoints on their own, just like they were with trapezium rule, and then we have 4 lots of the odd ordered y ordinates and 2 lots of the even ones. The other thing about this rule is that it only works when you have an even number of strips. Both of those things will become a little clearer when we look at the diagram. Because every parabola is mapped to 3 points on the curve, you need the first 3 points to be matched with a particular parabola, and then points 3, 4, and 5 get matched with the next one. So every 2 strips gets a parabola, basically. The first 2 strips gets a parabola, the next 2 strips gets a parabola, and that's why you need an even number of strips. The y2 value you'll notice here is on both parabolas. And that's why we treat the even ones differently to the odd ones. I'm not going to explain why ones are 2 and ones are 4 at this point. You need to go into the derivation in a bit more detail. But hopefully you can see why the odd number terms and the even number terms might need to be treated differently. Some of them, a little bit like with the trapezium heights, some of them are part of 2 parabolas and some of them are only part of 1 parabola. But here's the really cool thing about Simpson's rule. Not only does it model curves using curves, quadratics, but it can also be derived directly by taking a weighted average of mid-ordinate rule and trapezium rule. Turns out we get exactly the same formula. It's really neat. It does exactly what we wanted it to do. When we thought about trapezium rule and mid-ordinate rule, we realized that we need something which can combine the two so that the low values of mid-ordinate's rule can compensate for the high values of trapezium rule whenever the curve is convex. And when the curve is concave, the high value of mid-ordinate rule can compensate for the low value of trapezium rule. The largest source of error in both of those two rules come from the convex, concave, overshooting or undercutting, and those sources of error are completely eliminated by Simpson's rule. In general, you can get really incredible results from Simpson's rule. The reason we use it is not that we can't get the same level of precision with the other two, because we can, but we can get the same level of precision with a much smaller investment in time and computing power. So if we use this slightly different formula, we can end up with anything from 10 to 100 times better, depending on the function. Some functions will be modeled nicely with Trapezium Rule. Some of them really benefit from an application of Simpson's rule to make it work well. But we get a significant improvement in the precision of our answers for a much smaller outlay of computing time and effort. So this is our formula, basically. We take 2 helpings of mid-ordinate rule, because although mid-ordinate rule is low when trapezium rule is high and vice versa, the error in mid-ordinate rule is half that of trapezium rule. So Simpson's rule is essentially 2 helpings of mid-ordinate with 1 helping of trapezium. Here's a direct comparison between the 3 methods. So we can see how they all behave on the same function, x plus 2 sine x. The true value, incidentally, is 12.51328 something. So even trapezium rule does a reasonably good job here. Over this interval from 1 to 5, with 4 strips, we're getting an error of 0.35%. And it's a slight underestimate because the bits that undercut are more significant in this case than the bits that overshoot. With mid-ordinate rule, you can see that the effect is the opposite way round. So we have an overestimate, but by about half the size. So instead of 0.3 something percent, it's 0.17 something percent. And Simpson's rule comes along, combines the two, takes 2 helpings of mid-ordinate, 1 helping of trapezium rule, puts them together in a weighted average, and the overall effect is something which is now accurate to within 0.026%. And of course, just like with trapezium rule on its own, we can always increase the precision, increase the accuracy of our estimate by increasing the number of strips. So instead of using just 4 strips, if we'd gone on to use 8 strips, then that reduces the error for all of them. Trapezium rule ends up giving us a 0.086% error, but again, still an underestimate. Mid-ordinate rule is still an overestimate, but by about half as much. And Simpson's rule is right down to maybe 10 parts in a million. That's the level of error we're seeing there. 12.5135 instead of 12.5133, essentially. So we're accurate already to almost 3 decimal places. And all we needed was 8 strips. You can see why going up to 16 or 32 strips will often be sufficient to give you the level of precision that you need for almost any application. And if you need to have the same level of precision as your calculator will provide, well, Simpson's rule is probably the best way to do that. And you can get up to that level of precision by using no more than 100 strips in general. So it's worth remembering there are lots of different methods for numerical approaches to integration. Depending on the type of function you're dealing with, you might find that one of these works better than another one. But in general, if you want the most efficient method, Simpson's rule is going to be your go-to approach. If you want something that is sensible and works well with functions that have got a lot of straight line sections, then trapezium rule is going to work just fine. And in many ways, it's going to be more straightforward to calculate. And just to reiterate, for Edexcel A-level maths, you are not required to learn either of the second 2. You can forget about mid-ordinate rule, you can forget about Simpson's rule. The thing that you just need to make sure you're confident with is applying trapezium rule and understanding how that one works.